Well, good morning, everyone. It's great to be here. ICFP is, I was going to say ICFP is my favorite conference of the year, but that's not quite true. The Haskell Symposium is. But ICFP is a really close second. That's right. I'm going to continue the tradition that we had from yesterday about somebody from programming languages talking about AI things. My background is strongly in programming languages, semantics, those kinds of things. But as Mark was saying, for the past 3 years, I've been out at DARPA. And one of the things we're doing out there was looking at all sorts of technologies and the impact that they're having at the national level and how to move those technologies forward. And AI was a big part of it. I think I probably, over the past couple of years, spent about $400 million on AI kinds of projects. So I needed to get well into what these projects were doing to see how we move forward and why we move forward. And one of the things that struck me in that is this great irony that we have in formal verification and other ways of assuring systems, is that we just at the point of getting our arms around how we verify traditional kinds of systems. I remember about 10 or 12 years ago, Tony Hoare was going around with his grand challenge for verification. Let's be able to verify a compiler and things like this. And we've done that kind of thing. The community has succeeded tremendously. And we can bring verification technology as part of DevOps. I mean, it's really exciting to see how it's reached. But as I say, there's this irony that the moment we think we've got our hands around how to verify the systems that the world wants to build, the world is building very different kinds of systems. And frankly, we don't yet have any kind of handle on even how to think about verifying those things, as opposed to even being able to do it successfully. So my talk today is really about laying out, here's some of the challenges in this space. I'm hoping that some of the PhD students who are in the audience might get inspired by realizing there's a big problem space here, not very many people are working on it, I could make a huge impact. Maybe even some faculty get excited about, here's how I could sort of refresh some of the things that I'm working on. So let's just first of all think about assuring systems. This is the kind of way that we rail against often. Somebody designs a system, they implement it, and then there's the real world where they're testing it and they're running the system. And so if you want to know that the system is working well, you test it against that real system that's running there. You try it out in all sorts of places. And the question that keeps you up at night is, have I tested enough? And our community, of course, keeps saying, you can never have tested enough. But nonetheless, that's the question, have I tested enough? And we say what you want to be able to do is do some sort of proof that says you've done every possible case. And naively, you might think that we can get a complete answer, but we actually have a dual of this kind of situation, where we don't verify against the real system that's running on hardware with all the noise and all of those kinds of things that take place. We have a model of the system, and what we do is we verify against that model. And so the question that really should keep us awake at night is, how good is my model? How accurate is my model? There's that great phrase that in theory there's no difference between theory and practice, but in practice there is. And I think that's worth this community continuing to bear in mind. So the challenge always when we're thinking about verification is, how good is my model? And are there things in the real system that could slip in underneath my model? And so this is going to be motivate the question that will drive us throughout this talk, which is what kind of model do we have in mind when we're looking at AI systems? And how are we thinking of doing assurance against that sort of model? So I'd like to talk about AI systems much more generally. One of the things I had to do was communicate about what's going on in AI to all sorts of people, many of whom had no background in computing at all. And so I started using a narrative which talked about 3 different waves of AI. And so I'd like to run through some of that narrative with you, because I think it's a good way to get a bird's eye view of what's going on in AI and how we might think about AI. So first of all, the I in AI, the notion of intelligence. What is intelligence? It could be all sorts of things. The word is very rich in English, but I'm going to use intelligence to be about processing information, perhaps in subtle ways, perhaps in really delicate, intricate ways. So intelligence is fundamentally about what level of richness does one have to process information in what kinds of domains? And I find it useful to break that down, not just have a single scale, but to have a multi-dimensional scale. And so I've been using this sort of 4-dimensional scale just as a way to remember that there's different kinds of things going on in our ability to process information. How good might a system be at taking external input that might be noisy, all sorts of complications about it, and making sense of what's there, being able to understand in some sense what's there. So perceiving complex and subtle information. Another dimension of intelligence may be the ability to learn, the ability to adapt to a new situation, to figure out what's going on and do something with it. There's another rich form of intelligence, which is abstracting. You've seen the same thing again and again and again, and you say, oh, I now see a pattern, and you sort of jump up in a level of being able to think about things. It's the essence of mathematics. Essentially, what you're doing is you're seeing the same pattern again and again, and you're saying, what's the core stuff going on underneath that? And then reasoning, being able to say, well, if this happens and this happens and this happens, then I should do that and so on. So reasoning. Notice how different the sort of stuff that goes on in reasoning is from, for example, just perceiving and being able to make sense of data coming in. So if that's what intelligence is, then artificial intelligence is the programmed ability to process information in complex, rich, subtle ways. So I like thinking of intelligence as a scale rather than a bar that you have to get over. Some people would say, well, is that system intelligent? And I don't find that a helpful kind of question. I find it much more interesting to say what kinds of levels of what kinds of intelligence is being exhibited by a particular system. So as I say, I like talking about 3 waves of AI. They sort of line up a little bit historically, but it's much more by the sort of nature of the software that's going on. So the first wave of AI is handcrafted knowledge, where you're using particular sets of rules that may describe the way that a system works in practice. And I've given some examples of logistics planning. TurboTax, I think, is a great example. Even though it's old, a lot of people who are not specialists use something like TurboTax, and so they may be familiar with it. In TurboTax, I don't know if you have similar kinds of things in various countries in Europe. No, you don't do your taxes. That's right. It's done for you. In America, we have the joy of doing our own taxes. And so TurboTax is something that is able to, experts, accountants and tax lawyers and people like that sit down with the law, and they derive a lot of rules from the law about what happens in one situation, what happens in another situation. They codify that as a set of precise descriptions. And then TurboTax takes a whole bunch of input in, you type a bunch of things in, and then it figures out which forms to put it on. A lot of sort of rule-based reasoning going on with TurboTax. So in these kinds of situations, what happens is that people like you sit down and study the situation and figure out what is a rule that describes what's going on here. Chess is, again, another great example. There are rules about in this kind of position, this move is allowed. In this kind of position, this move is allowed. And then it does a lot of searching to be able to sort of figure out what's a good way forward. So when I say sets of rules, I don't just mean if then else kinds of rules. They could be statements in some rich higher order logic or something like that. But nonetheless, they're very precise kinds of rules that get applied in various situations. If we characterize, using our 4-dimensional scale, if we characterize the kind of intelligence exhibited by these systems, they're superb at reasoning. In fact, in chess-playing programs, if you do a human being against a chess machine, the chess machines are significantly stronger than human beings. Interestingly, just as an aside, combinations of humans and chess machines are even stronger than just one on the other, than just one on their own. But nonetheless, a lot of strength in reasoning, some ability to perceive. If I go back to TurboTax, I could just say, look over there for my employment form, and it will go and look at the employment form, and it will then extract a lot of data from that employment form and fill out the tax thing. But I couldn't sort of say to it something like, or it couldn't know, oh, there's a new law being passed, what should I do? How should I update my system? There's no ability of the system to reason. To learn based on new law. And indeed, nothing about abstracting. Like, I've seen this same pattern again and again and again. I've come up with a whole new way of thinking about taxes. I mean, the system just doesn't do that. Perhaps, fortunately, but it just doesn't do that. So this really, I think, quite well characterizes first wave systems. Think about your type systems. In some sense, your type system is a little bit like this. It's really good at doing reasoning about a mismatch between this part and that part. It may do a little bit of perceiving. In the case of a type system, perhaps it's like, oh, I realize you need it in this particular case rather than that. You haven't necessarily had to tell it everything explicitly. But there's very little ability in your type system to learn new patterns of behavior or things like that. When you're applying things to the real world, such as TurboTax or something like that, or logistics, it's an interesting question to say, what model are we assuring against? So I build some system with all sorts of rules. Now, is that set of rules my model? Or is there something higher level that corresponds to what my model is? I mean, it's an intriguing question. So, as I say, we'll keep coming back to this question. When we're applying things, particularly in the context of the real world, what model do we have in mind that is going to be used as the thing that we assure against? Just so that we're clear, I don't think there's any worry of it in this room, but just so that we're clear that first wave isn't old and stodgy and not relevant anymore. A couple of years ago, we hosted out in Las Vegas a cyber competition where the machines were doing cyber capture the flag against one another. And so they're all connected together, they all have a code base, and they're all analyzing the code within their code base, trying to find vulnerabilities. When they find a vulnerability, they look to see what's an automatic patch that they could apply to their vulnerability. They also look to see how might I exploit this vulnerability in one of the other machines and break in and be able to steal a piece of information. And so this was running, there's one quite exciting one quite exciting event that took place where one of these machines discovered a vulnerability in the code, so it knew it was in the other machines. It then figured out what's an exploit against that. It launched that exploit, it wrote the exploit, and then it launched it against another machine, successfully took over that machine, captured a piece of information. A third machine saw that exploit being launched, reverse engineered it, figured out what the fundamental flaw was in its own code that this exploit was going against, figured out how to patch that code, applied a patch, and became invulnerable when that exploit was then going to be launched against it. This whole time frame was 20 minutes. I mean, it's really kind of amazing when you see the power of reasoning systems applied to something like this. And these are first wave systems. These are systems with the kind of stuff that we do, a lot of static analysis, but also things like fuzzing and so on, code writing, all these kinds of systems. So first wave is still very exciting. But first wave has a challenge when you come to the real world, and one of those challenges is that the real world often isn't really sort of nice and clean and well organized in the way that we like our logical systems to be. And a great example of this was when DARPA was working on self-driving cars about 12 or so years ago. Back then, what DARPA was doing was pulling together technologies that had all been developed independently and saying, can we now put them in one whole system and have great success as this system works together? And so they had about 140, 150 miles of mountain, of sort of desert tracks, and they were driving from one place to the other out in western USA. 2004, none of the cars succeeded. In fact, I don't think any of the cars did more than 8 miles of this 140-mile track. And there were places where the organizers had to run up to the vehicles and turn them off because they looked like they were about to explode as the wheels were spinning and all sorts of things like that. They really were quite confused. The challenge was they're having to drive at 20 or 30 miles an hour. And driving at 20 or 30 miles an hour means that you're having to look maybe 50 yards, 100 yards ahead in order to be able to figure out what's out there and what you're going to do about it. And so on the camera input, there's a black splotch there. Is that a shadow or is it a rock? And in the end, it was really hard to write sets of rules which say, in this particular situation, that's a shadow. In this other particular situation, it's a rock. How do I steer? How do I take care of this thing? A year later, 5 of the cars completed, and one big difference between those was that they started using statistical techniques, in particular probabilistic programming, where they weighed up the probabilities of what they were seeing as being one thing or another. And I think this was a kind of harbinger of what was to come, that as you start seeing as you start processing the real world, you need to be much more statistical in the way that you handle it. And so this gives a good way to characterize then the second wave of AI, which is the wave that we're sort of in a big way just at the moment. This idea of statistical learning, where you have a huge amount of data, and on the basis of that huge amount of data, you figure out what the system should do. Now, a lot of people might naively say, well, the machine will just figure it out. It will learn what to do, as if there's some kind of magic going on there. And nothing could be further from the truth. It's not like that at all. Just in the same way as with first wave, where people sat down and figured out what are the sets of rules that are needed in a particular situation. In second wave, you need equally smart people to sit down and think, what is the underlying statistical framework that I need that will then get populated in an appropriate way as I get data coming through. So there's still a lot of engineering work to figure out how to build these kinds of systems appropriately. So the engineers create the statistical models for the particular problem domain that they're trying to address, and then they train them on big data. Now, when you look at the profile for intelligence here, it's a very different profile than we had with first wave. So way better on the perceiving, way better on the learning. But interestingly, just pure statistical methods are not very good at doing reasoning, of saying, let me follow this set of implications and see where this set of implications go. And so reasoning has gone way down, and still not very much on abstracting. But for the purpose of what we're talking about today, I think the really interesting question is the one that we've asked already. What is it that we're verifying against? Suppose I have a vision system. How do I, what does it mean to say I proved my vision system correct? I'm hoping that that question will keep you guys awake tonight. Like, what does it mean to prove that the vision system is correct? What are we assuring against? Well, there are some things that we could assure that the implementation of it is correct, and indeed there's great value there. There have been certain attacks against various systems because people hadn't handled things like underflow or overflow or not a numbers or things like that. So we could make sure that we verify that the implementation is correct, and indeed we'd be doing a public service to do that. But that's not really getting at the essence of what the problem is. Like, what does it mean to say that a system based on statistical learning is correct? So I don't have a full answer about it, but I think it's useful to think about the structure from a mathematical perspective of what's going on. And I find that the most helpful way to think about these statistical systems is to use something called the manifold hypothesis. So manifolds come from geometry. The idea is you have a space of information, data, if you like, maybe very high dimensional, and you may have a lower dimensional structure within that, and that lower dimensional structure might have certain properties. So the manifold hypothesis says that natural data comes in incredibly high dimensionally, but the features that you're interested in form low dimensional subspaces within that very high dimensional structure. So I think it's a really interesting way to look at these problems, and it may actually start to give us a handle on thinking about how to do assurance. Let's have a look at some examples of manifolds. So this 3D plot was actually taken, I think, something like tracking data from vehicles moving around or something like that. So it's naturally generated data that has been reduced down to a spherical three-dimensional form and then rotated. And the different colors are different kinds of things of interest. I actually have no idea what they are, but for the purposes of this talk, there's doesn't matter. You can see a lot of them form kind of stringy kinds of things in the 3D space. So that's like a one-dimensional subspace within this three-dimensional space. That kind of browny orange blob in the middle, if you look at it as it rotates a few times, it's actually not just an amorphous 3D blob so much as a bit more like an orange peel after you've peeled an orange, you know, in one go, and it's sort of curled in on itself somewhat. So it's almost like a two-dimensional space that's curved around itself. And so what we find again and again when we're looking at data like this is that high-dimensional data comes in, but the objects that we're interested in are these low-dimensional things, and we then are able to distinguish between them by separating these low-dimensional manifolds from one another and saying this part is in this manifold, this part is in this other manifold. And so we then need to look at how do we separate the manifolds. Let's take another example, a handwritten digit. So if I think about a digit, maybe for zip codes or postcodes, as a pixelated 28 by 28. So if it's 28 by 28, that's actually already 784 dimensional space. Like one image is 784 numbers. It's a vector in 784 dimensional space. So, and this is a fairly low dimensional piece of data compared with lots of things that we might be dealing with. So we have a particular image. It's an element within this high-dimensional data space. Now, if we look at the set of images, so there's a whole bunch of zeros up there and ones and twos and threes and so on. You could see that there's some sort of commonality between all the zeros, that you could imagine that they're kind of living in a very similar place to one another in this very large dimensional data space, and same with all the other digits. And so these, you could imagine some notion of these manifolds, 10 of these manifolds, somewhat distinct from one another, living in this very high-dimensional data space. And you might say, well, what's the dimension of these manifolds? They might be thicker lines, thinner lines, darker, lighter, these kinds of things. They may be twisted one way or another. The shapes may change. So they themselves may have, I don't know, 10 or 12 dimensions. There's a lot of variation. But nonetheless, that's just 10 or 12 dimensions as opposed to 784. On the right-hand side of the chart, what I've got is a graph of these 784 dimensions and how strong the pixels are in that. And I think that it's useful to have that chart because what I'm going to do is run through a whole bunch of these digits. So as I run through a bunch of the digits, don't so much look at the number at the top, but look at the chart at the bottom and see how that chart, it's remarkably unchanged as we go through. It's not just randomly jumping all over the place. And again, what it's demonstrating is that there's a high degree of coherency between all the various instances of something like the digit 8. So what we want to do is figure out how do we separate a manifold like this. So rather than work with 784 dimensions, I thought we'd work with 2 dimensions. And here are 2 one-dimensional manifolds in 2-dimensional space. And what we'd like to do is cleanly separate these. And you could imagine drawing a wiggly line around them saying this is how to separate them. But another way to do it is to actually morph the space itself. And so what we'll do is we'll stretch this space in various ways. We'll move it around. And as we're doing both linear and non-linear transformations to this space, stretching it, squashing it, stretching it, squashing it, and so on, you can see that we can morph the space in such a way that these 2 manifolds are quite now cleanly separated. And in fact, so cleanly separated that there's a linear separation between them, and we could just draw a single line which clearly separates these 2 manifolds. And so this is a general approach that gets used, that we have this high-dimensional space, low-dimensional manifolds within it, and we stretch and squash the space in interesting ways so that we can do clean cuts between across the space such that the manifolds that we're interested in lie in different spaces. Now you might say, but the problem is I might actually have a manifold contained within another. So if I take this picture of a target for archery, if I'm interested in the part of this image which is the middle of that, then no amount of stretching and squashing it will move it outside of the rest of it, unless I add an extra dimension. So if I add a 3rd dimension, now I can stretch and squash it in this other dimension, and I can again do a clean linear separation. So one of the things we'll find is that to be able to effectively stretch and squash spaces, we may have to add multiple new dimensions and then stretch and squash in those dimensions and then be able to do clean separation. And so this is the marvel of techniques like neural nets. This is exactly what they do. Now, a lot of people talk about neural nets based on the brain, modeling the brain, load of garbage. What neural nets really are Excel spreadsheets on steroids. So if I think about a neural net, a multi-sheet Excel spreadsheet, then what I do in each of the later sheets, so I put the data in on that first sheet, on each of the later sheets, what I'll do is a calculation just based on some of the cells of the earlier sheet. And I'll get a new calculation, and then I'll do it again, a new calculation, and so on. And it may be that each of the sheets from the first one is much larger than the initial. That corresponds to adding dimensions, because each data item, in some sense, corresponds to a dimension. So I'm adding extra dimensions. So each layer will act as doing a stretch and squash, until I get to the end, and I can do the computed outputs. And so staying in the Excel form, the kind of calculation that we do is just some sort of matrix multiplication followed by the application of typically a simple nonlinear function. The pos function is quite popular at the moment. The pos function says if the value is positive, leave it as it is. If it's negative, turn it to 0. And so you just need some nonlinear function for the thing to work. If you don't have a nonlinear function, you just have a series of linear transformations, then it would just collapse to a single transformation. So that's why you have to have nonlinear stuff going on in the middle. So the way that you build these then is that you just put random values in these, and you apply the first image to it, or whatever you're working with, and you say, how good was my assessment at the end? And you've got random values there, so of course it's terrible. What you then do is use calculus to work back and say, how should I shift some of those values in order to make something a little better than what I got the first time? And then you apply a new set of values, a new case of the data, a new image or whatever, and you do it again. And now you do that 50,000 times, 100,000 times, 1,000,000 times or whatever. And after you've done it a lot like that, it turns out that you start getting quite good results. Now, I have somewhat oversimplified. In reality, something just say for character recognition might have this kind of structure. One of the challenges when you have these lots of layers is that it's very hard for inaccuracies in the answer to propagate all the way back to the early layers. And so sometimes they might not move very much as you're propagating data back, so they're never likely to converge. Or they might swing widely and never likely to converge. So there are some ways that people have learned to say, let's put extra structure on these early layers to make sure that they converge sooner. So one popular thing is to make sure that all the weights in the early layers are the same, they're translationally independent. So for example, if I'm looking for your face in an image, I would like the thing to detect your face if it's here and if it's here. So there's no reason for the system to have very different values in different parts of the image. And so those kinds of techniques, those are called feature maps. So a feature map is looking for a particular small thing, maybe in essence some kind of abstraction of a line or an edge or something like that in the early parts. And it's looking for the same thing across the whole image. And then you get some sets of fully connected layers later on. So for the handwritten digits for zip codes in America, you'd need about 30,000 cells in a structure like this in order to get a high degree of accuracy. But the structure of this is one that there's no, I mean, there's cookbook rules, but like, how do you decide that this structure is better than another? Well, I tried 5 layers, it wasn't very good, so I did 6 layers, I got much better. Then I tried 7 layers, I didn't get any better, so I went back to 6. I mean, this is the kind of way that people think about these systems. So a system like this gets 99.5% accuracy. Why not 100%? Well, here are some example failures. This first one was a 5, but the system thought it was a 3. The second one was a 4, but the system thought it was a 9. The third one was a 9, but the system thought it was a 4. Or maybe it's the other way around. And that's kind of my point, that even for us as human beings, it's a little tricky to decide what the original writer of these scrolls intended them to mean. And that's the problem with natural data, that natural data itself is kind of inherently ambiguous. So what are we assuring against? Like, if the data itself doesn't even support sort of crystalline yes, no, true, false, like, what is the model that we're trying to assure against? So one of the things we've been trying to do is push hard on this, particularly in the statistical learning space, to figure out how do we get some greater sense of what's going on. One of the challenges that we have is that when I just have a learning process, I might start out with, let's take vision again, a vision system. It comes through, it's looking at an image, it says it's a cat. And you say, why do you say it's a cat? It says, well, I did my Excel spreadsheet calculation and cat turned out highest. It's not a very satisfactory answer. We would much prefer it to be able to say, here's some structure that's going on. That is, it's got fur, it's got ears. It's got this other feature that you guys don't seem to have a word for, but I see again and again and again. So something like that. And I think if we had systems like that, it would help with some of the challenges that we have in some of these AI systems where they may show bias, for example. There's gender bias, there's race bias, even in vision systems that show up. So understanding where that bias comes from, understanding why the model made the decision that it did, may help us to address some of those things. So I think it's really important for us to push hard on what's going on in the actual calculation itself and get some extra structure. But that doesn't get us all the way there to saying whether we can explain this. And if that's not bad enough, then you can start to put one neural system against another, one statistical system against another. And so you get incredible capabilities like this. So you might have a convolution neural net looking at the image and producing a set of abstract words, if you like. They don't correspond to anything directly in any language, but they're things that represent what's going on in the picture. And then you train a translation system to think of that as a language, and how do I translate that into, say, English? And so you get stunning examples of this, like the system looks at that image, a group of people shopping at an outdoor market, there are many vegetables at the fruit stand. And like, wow. I mean, it's really quite impressive. But sort of figuring out how that magic happens and when will that magic successfully happen and when won't it successfully happen is something of a challenge. Here's a great example of that. Like, no human being would ever say this of this picture. And you can get why the machine might have ended up in this space. But in some sense, that's no excuse. Like, how do you know that things like this aren't going to occur? So these systems are great in the aggregate, but individually, you can't necessarily rely on any particular case. Which, if we're using it to, say, catch terrorists, I mean, you really care about that kind of thing. Here's another kind of example. So this image on the left, a panda, the system would say with reasonable assurance that that's a panda. Then there's a pattern that was calculated from the neural net that got added to it. I don't know about you, but to me, these two images look pretty identical. And yet the system now with 99% confidence says that that's a gibbon. And so how do you have two images which to you and me look essentially identical, but the system has very differently? If you think about the underlying manifold, what's happened is that pattern was designed to knock it across that manifold boundary. And it was based on all sorts of things about the structure of the image and so on. It actually gets worse. Turns out that just knowing the approximate structure of the neural net, you can design a pattern which throws every image off. So there's a particular pattern that was based on just a particular structure of the neural net. and apply it to each of these images. You can start to see it appearing in this one that's the Indian elephant. You can see some images, they look like sort of interference lines or something like that has come in. And that's been enough to knock it out and move. So one pattern getting it put into these images moves it out. Here's another challenge. There was a really cool idea to say, how do we find out if malware is happening? One of the things that we might do is look at Twitter feeds. And so if you look at Twitter feeds, then you can start to notice that people are having malware on their machine before a company like Symantec realizes that there's this big malware problem going on. And so this chart says, how soon could you, if you were looking at Twitter data, how early compared with, here's a signature going out to your virus checker, how soon could you detect that malware? And it starts to get quite significant at about 25 days for the first tweet to appear, 25 days before malware gets really sort of recognized. Even if you are using something that waits till it detects lots of comments on Twitter before it sees this sort of emerging set of information, you're still maybe a week in advance of the official virus declaration. The trouble is something like Twitter is public data, and so the people who are constructing this malware also have access to the Twitter feed, and they could poison that data. That is, they could start putting adversarial tweets out there. That is, just by copying sets of tweets that other people have done at other times, knocks the precision of this system down to about 25%. So just the fact that other people can interfere with the data, the data itself is not something that you can necessarily rely on. People can get involved and shift it. And when it shifts, some of the assumptions that you might have had, some of the experimental data that you might have built up, is no longer entirely valid. And so that's problematic. When we think about trying to verify real systems, one of the things we've been working in directly, a few of the people in this room actually, is in how you use formal methods to create the software that goes into something like a helicopter. If I care about that, a lot of the same kinds of challenges that we've been seeing with AI apply in that kind of setting, where we start doing sort of model-driven development, and it reaches some kind of limitation. So let's walk through that as another example. So suppose I've got a physical machine, and in our case it was a Boeing Little Bird, unmanned Little Bird. So it's like the helicopters on MASH, for those of you who are interested in ancient history to watch TV like MASH. Some of us watched it like the first time it came around. So it's this like two-seater helicopter that you can carry all sorts of things with. So you have a physical machine, and what you do with that physical machine is that you build a model of that physical machine. You identify what are the key parts of this model, what are the moments of inertia, and it's a lot of physics at this point. How do things change if I change the angle on the rotors and things like that? I'll put them in wind tunnels, all sorts of things to build that. So I build a physical model of, a mathematical model of the machine, and I'll ask questions about, do I think I've seen everything significant about this? Once I'm confident about that underlying mathematical model, then I might design a control system for it. And in that control system, which will be based on various PIDs and other feedback kinds of loops, what I'll want to say is, to what extent am I confident that this will maintain flight correctly? Do I stay within a natural envelope? So I now have a control system designed to run this helicopter. And that control system has a nice, clean mathematical description. So from the physical machine, we're now in the world of mathematics, in the system identification, and now as we build the control structure, we're also in the world of mathematics. And so it's beautiful, we're in the world of mathematics, we can generate code, we can get controller code, and we've done this, formally generate controller code from the control system design, and you're guaranteed that control code is exactly reflecting what's going on in that controller system design. You install that control code on the machine. Every point of this, right back to the system identification, has been sort of mathematically guaranteed. So you put it on the machine, you fly it, and it flies like a dog. I mean, it's just rotten. And the problem is that however precise you are in building the model of the machine, it's not as accurate as the actual machine itself. And so then one of the things that we were doing was exploring, can you use machine learning at this point now to improve those parameters? You know, you've got some significant confidence that you're in the right vicinity of the code for this control system. But you now need to be able to improve those parameters by adjustment. Got a lovely video of this. Here's a little quadcopter. So in this quadcopter, it's got the control code in there, but it has no idea what its parameters should be. In fact, they're just set to random things. And the camera's watching this, and based on what it's doing, keeps sending it updates to how to improve. And so it's great when it starts sort of flying. It reminds me a little bit of a baby camel kind of trying to get up and stand on its legs and figure out how to be on its legs. And remarkably, in very short time, it figures out how to get these parameters right. Because the rest of the framework, you're confident that you've got the structure of the framework right, you're able to do some very interesting development of the system. The video has stopped. It's not that it's perfect at this point. There's other experiments. This was done out in California, not by us. In this situation, the question is, if I've got a system that is learning in real life how to do something, how do I take into account unexpected dangerous situations? So this is a quadcopter that is going to learn how to fly, do a whole bunch of parameter refinement. The trouble is, down at the bottom is a fan. And this is going to introduce a huge amount of complexity into the airflow that's going on. And so there's actually two videos overlaid on one another here. And in these two videos, one of them takes into account that if I get myself into a dangerous situation, I need to back off and learn outside of that situation before I go into the dangerous situation. Here we are about to come into the dangerous situation. And the one of them sort of moves away. Its fitness function tries to make sure it stays out of dangerous situations. The other is just trying to learn the best it possibly can in any situation, crashes into the ground a few times. A quadcopter, that's no serious problem. Might care differently, an Airbus aeroplane or something like that. So it's really useful to think about what do you want to build into the system as part of the fitness function, so as it continues to learn, what it's able to take into account and not take into account. See, I'm sure everybody is familiar with Microsoft's Tay bot. This was the most polite tweet that I could find online that came from this bot. So the history of this bot was that it had been launched originally, I think, in China, and ran there for ages, just great, and then in Japan, ran great, introduced it into America, and within a day, the hacking community had brought it down, essentially not by hacking any of the underlying code, but just by adversarial inputs to it. That is, thinking, how do I shift its learning model into a space that the designers did not intend? And so the training data that was, the live training data that was coming at it from live users led it into a problematic setting. So one of the frameworks I talked about, I said we're talking about 3 waves of AI, and I talked about 2, the first being rule-based systems, the second being statistical. But in practice, a lot of those things are now being used together, and this is what I like to characterize as the 3rd wave of AI, which has a structure a little bit more like this. So 3rd wave uses techniques from 1st and 2nd wave. We're still, I think it's fair to say, academically early in the notion of what 3rd wave systems are. We build lots of them, but we don't really understand what the fundamental design principles of these are. So in a 3rd wave system, you have things that are perceiving the outside world and building some kind of internal model for what's going on in the outside world, and then based on that internal model, maybe doing some reasoning about it. So think of a car driving system, for example. There may be lots of detectors doing lots of second wave stuff, and what they may be all doing as they're working together is building some sort of 3D model of what's the world, what's going on out there. Here are pedestrians, here are other cars, here's the edge of the road, and those kinds of things. And then based on all of that, doing things much more like first wave kind of decisions to say, what should I do in this particular setting? There's other cases where we do this, where the perceiving might be reading news reports and sort of making some assessment about what's the state of the world, and then making choices, doing reasoning based on what the state of the world is. So having some sort of contextual model that describes, here's what's going on, here's the system's view of the world. It's now broken the problem down into, how do I take external noisy input and reduce it to this model? And once I have this model, how do I make choices about how I move forward? And has a very different profile. Sort of has the best of both worlds kind of profile, if in principle, if you do this well together. And I think there's potentials here for us to think about assurance. It may be that something like this contextual model is the place where we start to hang some of our assurance arguments on and think about how the system is behaving based on that. Let me give it, I'll go back to handwriting. I'll give a quick example of something which is a little bit like that flavor, and this is in the world of probabilistic programming. So in the statistical learning that we saw before, the sort of neural nets, I start with an image and I process it by sort of pulling the space apart. And then I divide the manifolds and I say it was in that one, so it's going to be a 5 or something like that. With probabilistic programming, it works the other way around. It says, I know how people write, like with their hands, so they do a number of strokes. So any digit that I'm looking at will have been done with a number of strokes. And this is the nature of a stroke. Here's a typical stroke, here's another kind of typical stroke. And so you look at the trajectories of strokes, you sort of describe what the hand might do. And that's now a sort of unparameterized model for what it means to be writing something with a pen. And then you give it training data, and actually you can often do just one single example of training data in this case, where here's a 0, here's a 1, here's a 2. And what it will do is it will fill out the parameters in that model a little bit like a control system in some sense. It's like it's tuning the parameters of the control system. And that creates this thing called a generative model. And the generative model doesn't work by parsing the image and sort of separating the manifolds and figuring out where they go. It actually works the other way around. It sort of says, if I was trying to write a 9, how similar to this would it be? If I was trying to write a 4, how similar would this be? So it's sort of going the other way around. It's going from the model of what it's looking for to the thing that it's seeing. And it's trying to figure out how likely the mark that's on the paper was reflecting an intent for a 9 or reflecting the intent for a 4 or something like that. So that's quite cool. Another thing that we need to think about as we're thinking about these third wave systems is to say, how do we actually convey our intent to one of these systems? So one of the aspects of this is you might think about, how do I want to express what the system should do? I could tell it to do things, so that's one choice. There's lots of choices here, and this is a slide of choices. Another one is I could tell it what not to do, and maybe I do both, like do this kind of thing, but definitely don't do that kind of thing. I might define behavior in terms of scores. I might define behaviors in terms of preferences. So I might have lots of things to describe how behaviors go. Now the question is, to what extent does that reflect what I actually want? I've abstracted it into some kind of model. I might be able to say, now my system follows all these preferences. But how good are those preferences? And then there's the, one of the beauties of the learning systems is you don't describe, this is what eyes are like, and so measure how far apart they are. This is what a nose is like. There's none of that. The system extracts some of these. And a similar kind of way that if I have a household robot that I want to do chores, I don't want to program it on my keyboard. I want to show it, this is how you make tea. Like, that's the right color. This is the wrong color. and things like that. Of T, I mean, of course. So being able to sort of show it ways, have some sort of two-way interaction, I think very, very valuable. The military, I think, has got some interesting examples of this. So submarine commanders, when they're learning how to be a submarine commander, they're essentially an autonomous system separated from the upper command because they may not have radio communication. So they have sets of instructions like this. And if you look at the nature of these instructions, you can see that they overlap in places, that they're slightly contradictory in places. And so I understand that one of the things that happens with submarine commanders is the first couple of times that they're out there trying to do things, they may be in rapid communication, but then they start becoming more and more autonomous as they've sort of now are learning how to interpret some of these instructions. And then depending on their ability to sort of go through that learning curve depends on whether they gain the trust of the people back home. So it could be that we need to figure out how to have instructions like this. I'm not worried about the natural language form of it, but if you abstract it out, like what is the kind of way that we should be instructing the various systems that we have in order to be able to communicate intent in these incredibly complex worlds that we want things to work. A couple of lessons that we come from this is, first of all, if the system thinks it absolutely knows what you intend, then it's going to be wrong. Because, I mean, in some sense, we don't even know exactly what we intend. Like, if you just try to describe how you drive your car, you'll find that it's immensely detailed. All the specifications that we have about these kinds of things are incomplete. And then I think it's really important that things handle different kinds of communication styles, because the way I want to explain something is going to be different from the way you want to explain or show something. So let's come to just conclusions and wrap up at this point. So here are some conclusions. We start to think, what are we trying to assure? What model are we assuring against? As I say, I've laid out challenges for us to think about it, some sort of structure of this space. I'm hoping that this will stimulate some thought. There's all sorts of problems that we have to cope with. Already we have systems where mistakes in the AI system leads to things that are undesirable. And people are able to exploit these in all sorts of ways. You might have emergent behavior. There's this thing happens that when you take a system and you build a very complex system, that you essentially create a new world that never existed before, and the rules and behaviors in that world may be almost impossible to predict from the underlying rules and behaviors. Which of us could have predicted biology just from knowing the periodic table and the behavior of the atoms? I mean, it's so complex, and potentially there were lots of different biologies that could happen. Once you get higher level, of course, you may have that the AI system has its own goals and intents and is trying to carry things out. How do you know that those goals and intents reflect the owner, operator, whatever the right word is, of the machine? So I'm going to stop at that point and open it up for questions. Thank you.